The multiverse is the hypothetical set of finite or infinite possible universes, including the universe we live in. Together, these universes comprise everything that exists. The entirety of space, time, matter, energy, and the physical laws and constants that describe them. The various universes within the multiverse are called parallel universes, or alternate universes. The American philosopher and psychologist William James coined the term multiverse in 1895, but in a different context. Explanation: the structure of the multiverse, the nature of each universe within it and the relationships among these universes depend upon the specific multiverse hypothesis being considered. Multiple universes have been hypothesized in cosmology, physics, astronomy, religion, philosophy, transpersonal psychology, and fiction, particularly in science fiction and fantasy. In these contexts, parallel universes are also called alternate universes, quantum universes, interpenetrating dimensions, parallel dimensions, parallel worlds, alternate realities, alternate timelines, and dimensional planes. The physics community continues to debate the multiverse hypothesis. Prominent physicists disagree about whether the multiverse might exist or is not even a legitimate topic of scientific inquiry. Serious concerns have been raised about whether attempts to exempt the multiverse from experimental verification could erode public confidence in science and ultimately damage the study of fundamental physics. Some have argued that the multiverse question is philosophical rather than scientific because it lacks falsifiability. The ability to disprove a theory by means of scientific experiment has always been part of the accepted scientific method. Paul Steinhardt has famously argued that no experiment can rule out a theory if the theory provides for all possible outcomes. In 2007, Steven Weinberg suggested that if the multiverse existed, the hope of finding a rational explanation for the precise values of quark masses and other constants of the standard model that we observe in our Big Bang is doomed, for their values would be an accident of the particular part of the multiverse in which we live. Supporters and opponents. Supporters of one of the multiverse hypotheses include Stephen Hawking, Brian Greene, Max Tegmark, Alan Guth, Andre Linde, Michio Kaku, David Deutsch, Leonard Susskind, Raj Pathria, Alexander Vilenkin, Laura Mersini Houghton, Neil deGrasse Tyson, and Sean Carroll. Scientists who are opponents of the multiverse include Nobel laureate Steven Weinberg, Nobel laureate David Gross, Paul Steinhardt, Neil Turok, Vyacheslav Mukhanov, Michael S. Turner, Roger Penrose, George Ellis, Joe Silk, Adam Frank, Marcelo Gleiser, Jim Baggott, and Paul Davies. Classification schemes. Max Tegmark and Brian Greene have devised classification schemes for the various theoretical types of multiverse, or for the types of universe that a multiverse might comprise. Max Tegmark's four levels. Cosmologist Max Tegmark has provided a taxonomy of universes beyond the familiar observable universe. The levels according to Tegmark's classification are arranged such that subsequent levels can be understood to encompass and expand upon previous levels, and they are briefly described below. Level 1. Beyond our cosmological horizon, a generic prediction of chaotic inflation is an infinite ergodic universe, which, being infinite, must contain Hubble volumes realizing all initial conditions. Accordingly, an infinite universe will contain an infinite number of Hubble volumes, all having the same physical laws and physical constants. In regard to configurations such as the distribution of matter, almost all will differ from our Hubble volume. However, because there are infinitely many, far beyond the cosmological horizon, there will eventually be Hubble volumes with similar, and even identical, configurations. Tegmark estimates that an identical volume to ours should be about 1,010,115 meters away from us. Given infinite space, there would, in fact, be an infinite number of Hubble volumes identical to ours in the universe. This follows directly from the cosmological principle, wherein it is assumed our Hubble volume is not special or unique. Level 2. Universes with different physical constants in the chaotic inflation theory, a variant of the cosmic inflation theory. The multiverse as a whole is stretching and will continue doing so forever, but some regions of space stop stretching and form distinct bubbles, like gas pockets in a loaf of rising bread. Such bubbles are embryonic level 1 multiverses. Lingd and Van Turing calculated the number of these universes to be on the scale of 101,010,000,000. Different bubbles may experience different spontaneous symmetry breaking, resulting in different properties such as different physical constants. This level also includes John Archibald Wheeler's oscillatory universe theory and Lee Smolens's fecund universes theory. Level 3. Many worlds interpretation of quantum mechanics. Hugh Everett's many worlds interpretation is one of several mainstream interpretations of quantum mechanics. In brief, one aspect of quantum mechanics is that certain observations cannot be predicted absolutely. Instead, there is a range of possible observations, each with a different probability. According to the MWI, each of these possible observations corresponds to a different universe. Suppose a six-sided die is thrown and that the result of the throw corresponds to a quantum mechanics observable. All 6 possible ways the die can fall correspond to 6 different universes. Tegmark argues that a level 3 multiverse does not contain more possibilities in the Hubble volume than a level 1-2 multiverse. In effect, all the different worlds created by splits in a level 3 multiverse with the same physical constants can be found in some Hubble volume in a level 1 multiverse. Tegmark writes that the only difference between level 1 and level 3 is where your doppelgangers reside. In level 1 they live elsewhere in good old three-dimensional space. In level 3 they live on another quantum branch in infinite-dimensional Hilbert space. Similarly, all level 2 bubble universes with different physical constants can in effect be found as worlds created by splits at the moment of spontaneous symmetry breaking in a level 3 multiverse. According to Yasunori Nomura and Raphael Busa and Leonard Susskind, this is because global space-time appearing in the inflating multiverse is a redundant concept. This implies that the multiverses of level 1, 2, and 3 are, in fact, the same thing. This hypothesis is referred to as multiverse equals quantum many worlds. Related to the many worlds idea are Richard Feynman's multiple histories interpretation and H. Dieter's many minds interpretation. Level 4. Ultimate ensemble. The ultimate ensemble or mathematical universe hypothesis is the hypothesis of Tegmark himself. This level considers equally real all universes that can be described by different mathematical structures. Tegmark writes that abstract mathematics is so general that any theory of everything that is definable in purely formal terms is also a mathematical structure. For instance, a TOE involving a set of different types of entities and relations between them is nothing but what mathematicians call a set theoretical model, and one can generally find a formal system that it is a model of. He argues this implies that any conceivable parallel universe theory can be described at level 4, and subsumes all other ensembles. Therefore brings closure to the hierarchy of multiverses, and there cannot be, say, a level 5. Jürgen Schmidhuber, however, says that set of mathematical structures is not even well defined, and admits only universe representations describable by constructive mathematics, that is, computer programs. He explicitly includes universe representations describable by non-halting programs whose output bits converge after finite time, although the convergence time itself may not be predictable by a halting program, due to Kurt Gödel's limitations. He also explicitly discusses the more restricted ensemble of quickly computable universes. Brian Greene's 9 Types. American theoretical physicist and string theorist Brian Greene discussed 9 types of parallel universes. Quilted. The quilted multiverse works only in an infinite universe. With an infinite amount of space, every possible event will occur an infinite number of times. However, the speed of light prevents us from being aware of these other identical areas. Inflationary. The inflationary multiverse is composed of various pockets where inflation fields collapse and form new universes. Browner. The Browner multiverse follows from M theory and states that our universe is a three-dimensional Browner that exists with many others on the higher dimensional Browner or bulk. Particles are bound to their respective brownness except for gravity. Cyclic. The cyclic multiverse has multiple brownness that collided, causing big bangs. The universes bounce back and pass through time, until they are pulled back together and again collide, destroying the old contents and creating them anew. Landscape. The landscape multiverse relies on string theory's Calabi-Yau shapes. Quantum fluctuations drop the shapes to a lower energy level, creating a pocket with a different set of laws from the surrounding space. Quantum. The quantum multiverse creates a new universe when a diversion in events occurs, as in the many worlds interpretation of quantum mechanics. Holographic. The holographic multiverse is derived from the theory that the surface area of a space can simulate the volume of the region. Simulated. The simulated multiverse exists on complex computer systems that simulate entire universes. Ultimate. The ultimate multiverse contains every mathematically possible universe under different laws of physics. Cyclic theories. In several theories there is a series of infinite, self-sustaining cycles. M theory. A multiverse of a somewhat different kind has been envisaged within string theory and its higher dimensional extension, M theory. These theories require the presence of 10 or 11 space-time dimensions respectively. The extra 6 or 7 dimensions may either be compactified on a very small scale, or our universe may simply be localized on a dynamical dimensional object, a.d. Browner. This opens up the possibility that there are other brownness which could support other universes. This is unlike the universes in the quantum multiverse, but both concepts can operate at the same time. Some scenarios postulate that our Big Bang was created, along with our universe, by the collision of two brownness. Black hole cosmology. A black hole cosmology is a cosmological model in which the observable universe is the interior of a black hole existing as one of possibly many inside a larger universe. This includes the theory of white holes, of which are on the opposite side of space-time. While a black hole sucks everything in, including light, a white hole releases matter and light, hence the name white hole. Anthropic principle. The concept of other universes has been proposed to explain how our own universe appears to be fine-tuned for conscious life as we experience it. If there were a large number of universes, each with possibly different physical laws, some of these universes, even if very few, would have the combination of laws and fundamental parameters that are suitable for the development of matter, astronomical structures, elemental diversity, stars, and planets that can exist long enough for life to emerge and evolve. The weak anthropic principle could then be applied to conclude that we would only exist in one of those few universes that happen to be finely tuned, permitting the existence of life with developed consciousness. Thus, while the probability might be extremely small that any particular universe would have the requisite conditions for life to emerge and evolve, this does not require intelligent design as an explanation for the conditions in the universe that promote our existence in it. Search for evidence. Around 2010, scientists such as Stephen M. Feeney analyzed Wilkinson microwave anisotropy probe data and claimed to find preliminary evidence suggesting that our universe collided with other universes in the distant past. However, a more thorough analysis of data from the WMAP and from the Planck satellite, which has a resolution 3 times higher than WMAP, failed to find any statistically significant evidence of such a bubble universe collision. In addition, there is no evidence of any gravitational pull of other universes on ours.